If all the air is in the corner of the room, for example, then you know more about the positions of the individual particles. They're all in the corner of the room, versus if they're spread through the room. But it took the invention of information theory to really see the connection between information and entropy. It was Claude Shannon who founded the field of information theory and also invented the entropy of information, Shannon entropy. Shannon entropy can be thought of as the amount of hidden information in a system, or more precisely, the amount of information we can hope to gain by making a measurement of the system. By Rolf Landauer in 1960, nearly 100 years after Maxwell proposed the conundrum. Landauer's principle states that any logically irreversible manipulation of information, such as the erasure of a bit or the merging of two computation paths, must be accompanied by a corresponding entropy increase. And this has come to be seen as a fundamental limit to the efficiency of computation. Both Maxwell's conundrum and Landauer's resolution are fascinating because they highlight the fundamental link between entropy and information. Firstly, they show that information about a system allows us to extract useful work. Claude Shannon, the father of information theory, was deeply inspired by the close connection between entropy and information. He defined a new type of entropy, Shannon entropy. It can be interpreted as the amount of previously hidden information that can potentially be revealed by the observation of a random event. In a sense, it's a measure of the uncertainty of the event. The more uncertain or more unusual an event, the more revealing it is than a more predictable event. So for example, the roll of a die has more entropy than the flip of a coin. There are more potential outcomes in the former, so more uncertainty has been eliminated when the die is cast. Shannon used the term entropy for this measure because his formula was almost identical to the formula for thermodynamic entropy. Just multiply by the Boltzmann constant to get the latter. If you take all possible results of the die roll to be equally likely, then Shannon's formula looks just like the Boltzmann equation. This isn't a coincidence. In fact, Shannon entropy is, in a sense, just a generalization of thermodynamic entropy. The former describes the amount of hidden information in any system, the latter applies specifically to thermodynamic systems. And there's a third, perhaps even more fundamental type of entropy. That's quantum entropy, also known as von Neumann entropy. It describes the hidden information in quantum systems, but more accurately, it's a measure of the entanglement within quantum systems. In fact, the evolution of quantum entanglement may be the ultimate source of entropy, the second law, the limits of information processing, and even the arrow of time. We'll get tangled up in all of that in an upcoming episode of Space-Time. We need to understand what entropy and the second law emerge from. What underlying property of nature do all these different definitions of entropy describe? As is often the case, getting more fundamental means getting quantum. And there is indeed a type of entropy that applies to quantum systems, like our air molecule. It's von Neumann entropy. And understanding it may help us understand not just the second law, but also the arrow of time, and how the large-scale world emerges from the quantum world in the first place. Maybe the answer is not to build tiny experiments or giant colliders, but to make the quantum world big enough to meet gravity and the classical world halfway, perhaps inside a regular laboratory. The known laws of physics can be pretty clearly broken up into these two realms, those describing the large-scale classical world and the tiny quantum world. Classical physics works great above about a micrometer, where objects are made of many, many atoms. Everything larger is, as we say, macroscopic. Quantum mechanics rules below the nanometer scale, at single molecules and atoms and smaller, but the in-between scale, the mesoscale, feels both of these worlds. It is, as we say, semi-classical, behaving mostly classically in some ways, but exhibiting quantum effects in certain conditions and when carefully coaxed. Today, we're going to look at approaches and some example experiments for probing fundamental questions by looking at this intermediate space where both classical and quantum mechanics are at play. Maybe we don't have to wait for that solar system-sized particle accelerator to do this cool stuff. We'll look at two paths. One is to look for a breakdown in our classical understanding of gravity at the mesoscale. The second will be to look for true quantum effects in as large a system as possible, but also in the mesoscale. So we're going to try to make gravity small and then make quantum big. If we can get them to meet somewhere in the middle, maybe we can even make gravity quantum. Let's start with an experiment so elegant and simple that it's been our go-to for measuring the strength of gravity since we, well, first tried to measure the strength of gravity.